Is that what you guys agree?
Well, it depends. I mean, thermodynamically you'd want to, but what does that do to the rate?
What does that do to the rate? That's a great question. All right, so let's take 3 examples. T0, and we'll just say that this is less than, obviously, some other T0, less than some other T0, right? We'll call them, in the notes he's got them as T03, T02, T01. So what's another plot that I can make is conversion. Now though, instead of putting temperature on the x-axis, I'll put volume. And let's pretend that we have some finite reactor. Whatever, doesn't matter. So what does the first curve look like? Let's ask ourselves 2 questions. Where will it stop? And how fast will it get there? So it's going to stop at the equilibrium conversion. So if I'm here, I'll draw this line over, and we'll pretend that I had these flatter than I did. We're going to say this is xe1. Right? And so now how quickly will it get there?
Quickly.
Let's just say, yeah, really fast. So what's the shape going to look like? Well, remember that the rate will decrease as conversion increases. Yeah, it's going to have a shape like that, but it's going to, stop growing, essentially. And where it bends over, that is the equilibrium. So that's what you get. Okay, so this is T01. All right, what about T02? So it's going to end up here. I didn't really finish this one, did I? It's going to end up here. Does it get there faster or slower?
Well, I'll sign this up.
Slower, right? It's at a... Sorry, this is 2. And let's say this is what I get for the third initial temperature. So we cooled it down to 5 Kelvin. And in 300 liters, you got maybe 2% conversion or something. Because at 5 Kelvin, you need a massive reactor in order to get to equilibrium. There's no guarantee that you're going to get to equilibrium for any of these reactions. It depends on the size of your reactor. So when you're thinking about, yeah.
Couldn't you have a smaller reactor if you really slow down those flow rates?
Of course, right. It's residence time. It's not the size of the reactor, it's the amount of residence time. Now there's physical limitations on how slow you can pump fluid. And there's physical limitations on how big you can make a reactor. So you're obviously battling those 2 considerations. So again, what you have to consider here is you have 2 factors that you're fighting against. The hotter it is, the harder it is to get to a high temperature, a high conversion, because you're equilibrium limited, not because you're rate limited. But if you cool down too much, you'll become rate limited, where you don't even see equilibrium. Equilibrium's another 3,000 liters away. That make sense? What about...
Wait.
Yes, I don't need the notes anymore. I'm just making stuff up at this point. What about... for an endothermic reaction? Then what's the optimal feed temperature?
Service or the sun?
As high as you can go.
Yeah, as hot as you can get it before you start reaching issues with safety or economic issues, right? That also has a consideration.
So the service of the sun.
But yeah, now kinetics and thermo favor increasing the temperature. Whereas for an exothermic reaction, there's a competition between those two things. Okay, so now, thank God, I'm leaving this podium. I brought last time's lecture notes and next time's lecture notes. And somehow left off today's. Oh, by the way, I had to send one of you guys back to the office with keys if I didn't have it on Dropbox. I probably should have done that anyways. All right. So for the most part, we've been working with CSTRs. If there was anything that involved me asking you for a volume or asking you for an equilibrium within a specified volume. So far, we haven't tackled that with a PFR. Of course, we did just do a problem with a PFR, but we sidestepped the volume issue. We said they're big enough to achieve 95% of equilibrium conversion. So you guys didn't have to worry about the design equation for that problem. So now let's worry about it. Okay, so if it's adiabatic, what's changing as we go in and out? Temperature, right? And it changes now as a function of distance along the length of the reactor. What does that remind you of? Doesn't conversion change the same way for a PFR, right? As you go down the length of the reactor, the conversion changes. Same thing here. As you go down the length of the reactor, now the temperature's changing. And those two things are related. The higher the conversion, if it's exothermic, the higher the temperature. Okay, so what's our energy balance? Steady state. And now what version we choose to use, obviously we kind of bounce around. So we're just going to go ahead and have theta times the heat capacities out minus in plus the conversion times the delta H of reaction at the temperature that at this temperature that's varying along the length of the reactor. And then the design equation for a PFR. Right? And now rate is a function of both conversion, like it was before, but also temperature. And we have to solve simultaneously the energy balance equation, which is not differential, so that's nice, but still messy, and then this differential equation at the same time. And like I said, we're going to talk about the mechanics of that next time we're not talking about the test. what you end up with is, and again, whether you do this numerically or however you do it, you end up with x and t both as a function of volume. And that's what you're going to see. When we do this in Excel, we're going to plot conversion versus volume, temperature versus volume. That's simple.
And we're talking about reactor volume, right?
Yes.
So with reactor volume, are we basically saying it's a plot, since the cross-sectional area is the same, it would just be versus length?
Yeah, you can also plot it versus length if you wanted to or needed to, or yeah. But yeah, the cross-sectional area is not changing, so you can relate volume to length.
As one function? Like, or as two
Say that
functions,
again.
As two functions or one function?
You mean, these are going to be two different plots.
It's just we only have one differential equation, and it's for two variables. That's not b.
Yeah, but sure, we have temperature as a function of conversion. So we get x versus volume, and then we just, but again, we're not going to get it analytically. So, you know, we're going to get conversion as a function of volume, and then from that we can calculate the temperature as a function of volume through calculating temperature as a function of conversion. That's the only reason why the temperature is changing, is a conversion. Okay, there's another way to do it. I don't know. So in the book, they talk about, in chapter 11, solving this in a non-numerical method that's still numerically based. But essentially in the book, he says, go ahead and pick a temperature. From that, you can get the rate constant and the delta H of reaction. And from that, you can get a rate. And from that, you can get 1 over the negative of the rate. Why do we get 1 over the negative of the rate? Levenspiel, right? So you do this 20 times.